All right, let's dive into two of the most powerful and, yeah, sometimes confusing concepts in JavaScript, scope and closures. But I promise, stick with me because by the end of this, you're going to see these as a legit coding superpower.
So, let's start with a little bit of a puzzle. Picture a function. It runs, it does its thing, and then it's done. Poof, gone. But what if I told you it could somehow remember things? How can a function hold on to information, like a variable, long after it's finished executing? I know, it sounds impossible, but that's the whole secret we're going to unlock today.
And the answer to that puzzle is a feature called closures. It's not actually magic, but honestly, it feels a lot like it. A closure is what gives a function this incredible memory. But to really get how this superpower works, we first need to figure out where our variables even live in the first place.
And that brings us to scope. Just think of scope as the rule book that decides where your variables can be seen and used in your code. It's kind of like the home address for your data. Understanding this is absolutely the most critical first step.
First up, you've got the global scope. This is the big, wide-open country of your program. Any variable you declare way out here, not inside any function, is global. That means it can be seen and used from literally anywhere in your code. Just a word of warning, though. It's really easy to cause problems and conflicts out here. So as a general rule, we try to keep the global space pretty clean.
So check this out. It's a really simple idea, but it's super powerful. We declare global var at the very top level. Then, inside our showGlobal function, we can just reach out and grab it, no problem. It works because that function can see everything in its global neighborhood. Okay, let's shrink things down to a more private space, function scope. Now, if you declare a variable using the var keyword inside a function, that variable is trapped. It can only be seen and used within that one specific function. This is a bit of an older way of doing things, you'll see, but it's still crucial to know how it works.
And this code, it shows that boundary perfectly. Inside the example function, function var is alive and well, totally accessible. But the second we step outside that function and try to log it, bam, we get an error. It's because out there, it just doesn't exist. It's totally private to the function.
And that brings us to the modern way, block scope. This was introduced with let and const, and it's even more precise. A variable declared this way is only accessible inside the set of curly braces, the FG, where you defined it. That could be a function, sure, but it could also be an if statement or a for loop.
Take a look at this if statement. Inside those curly braces, block var is totally fine. We get the little green check mark. But step just one line outside of that closing brace and boom, error. The key takeaway is that those curly braces act like a force field for variables that you declare with let and const. Okay, so let's put them side by side real quick. Var gives you function scope, which is pretty broad, but let and const give you this much tighter, much more predictable block scope. And that precision helps you avoid all sorts of weird bugs. It just leads to cleaner, safer code. That's why you see let and const everywhere in modern JavaScript.
Okay, so we know where variables can live. But how does a function know which variables it's allowed to see? Well, the rule for that is called lexical scope. Now, I know, lexical scope sounds kind of fancy, but the idea behind it is actually super simple. A function's access to variables is decided by where you physically write that function in your code.
Right here, we've got an inner function that's nested inside an outer one. Because of lexical scope, that inner function can look outside of itself and see the name variable that belongs to its parent, the outer function. It's kind of like a one-way mirror. The inner function can see out, but the code on the outside can't see in.
And that brings us right back to our original puzzle. See, we've got all the pieces now. Scope defines the boundaries. Lexical scope defines the rules of who can see what. So now, let's combine them to build a function that can actually remember things. Let's finally unlock the magic of closures.
Okay, pay close attention to this one, because this is where it all comes together. The outer function is doing something really clever. It's not returning a value like a number or a string. No, it defines another function, inner, and then it returns that entire function. We're basically capturing the inner function and its whole environment.
So let's just walk through what happens. Let's say we run this code. Const getSecret equals outer. Okay, step 1, outer gets called. Step 2, It creates and returns the inner function, which we've now saved. Now step 3, outer is finished, right? So its secret variable, logically, should be gone forever. But, and this is the magic part, when we call our getSecret variable later on, it still remembers and can access the secret variable. How is that possible?
This is a closure. The inner function basically formed a bond, a closure, over the scope of the outer function. It packed up all the variables it might need from its parent, in this case the secret variable, and carried them with it in a sort of memory backpack. So even when the parent function is long gone, that inner function still has its backpack full of variables.
Okay, this is super cool, but what's the point? Like, what can you actually build with this? Let's look at a couple of really powerful real-world examples that you can start using in your own code right away. So here's a classic example, creating private variables. We can build this counter function that has a local count variable tucked away inside it. It then returns an object with methods to increment the count and get the count. Because of the closure, that count variable is completely hidden from the outside world. The only way to change it is by using the methods we decided to provide. If you try to access it directly, like c.count, you just get undefined. That's data privacy in action right there.
And here's another awesome pattern, factory functions. This make multiplier function is like a little factory that produces other functions for us. When we call make multiplier 2, it spits out a brand new function that has remembered, through a closure, that its factor is 2. We can use this to build any number of specialized functions on the fly, each with its own little memory.
Okay, you've seen the theory, you've seen the practice. Now it's time to really make this stick and put that superpower to work yourself.
So now it's your turn. Can you write the functions that would make this code work? The first challenge is to create a track function that uses a closure to remember how many times it's been called. The second one is to create a greetAlice function that remembers the name you give it. Go ahead and pause here and give it a shot. Seriously, try it out. So let's do a super quick recap of the key takeaways. Scope is all about where your variables live. Lexical scope means inner functions can peek into their parent's world. And a closure, that's when a function remembers that parent's world, carrying it around in that memory backpack even after the parent is gone. And we can use this for awesome patterns like private data and function factories.
And that leaves us with one final thought. Now that you understand how to give your functions a memory, the possibilities are just endless. So I'll leave you with this. What other amazing memory-powered functions could you build? What kinds of problems can you solve now?